All right, so welcome to the first lecture on nonlinear elasticity. Like I said, this is a challenging course with a lot of notions that come together finally to help you understand and model soft matters, soft solids, which are all around us in the world, the engineering world, the scientific world, and the natural world. Today we're going to start with some reminders about some notions of linear algebra and that you might have seen before, that you must have seen before, I hope, such as scalar and vectors. I go through in a sense, a crash history on of nonlinear elasticity. It's not that old a science, a topic, if you want. You could go back to, I guess, to Cauchy, people like that, but really it came on its own in the 1950s and has been going through ups and downs. In the early days, in the 50s, it was used to model rubber because that was a huge industry. Then, I guess, 20, 30 years down the line, the scientists were more or less happy with their description of rubber, and the discipline seemed to go through some sort of I guess, neglect or maybe a downturn. But then in the 90s and 2000s, there was a rebirth because of interest from biologists and medicine and disciplines like that, who realized that it provided a great framework to describe the behavior of soft tissues. All right, so let's just start. So algebra. Okay, so if you think about it, so far you've used algebra or algebraic notions, algebraic objects to describe the physical world, right? Typically, what you've seen is scalar quantities, say for time, mass, temperature, that kind of thing. That's just a number. Presented one number. Yeah, and that was fine for those physical concepts, but pretty soon, already, I guess in first year, you realize that that wasn't enough. There was some phenomena that you couldn't describe only with scalars, and we had to introduce what's called vectors. And originally, it was for the velocity. If you remember, we needed vector quantities, and then we developed a whole algebra, adding vectors, subtracting vectors, taking products, whatever that meant, dot products, cross products, so on and so forth. And vectors, they were represented by one array of numbers. Right? So if we were in a three-dimensional world, for instance, there was three components. So if you had vector A, you had A1, A2, A3, were the three components of the vector. And that was very useful for, like I said, velocity, but also moments and forces and many concepts that are perfect and sufficient to describe a huge proportion part of mechanics and other physics, right? Well, in this course, we're going to see that, again, we have to go one step up, that vectors won't be enough to describe everything we need to talk about nonlinear elasticity. We have to introduce new concepts, new objects, and the one step up is the so-called tensors, represented by two arrays of numbers. All right, and the way we're going to do that is using matrices. So matrices is going to have two indices. Matrix A will have components A, I, J, and I will go from 1 to 3 and J from 1 to 3. So it's going to be 9 components for a tensor. So in this course, what we tensor are those quantities that can be represented by a matrix. If you study the semantics, the real, how should I say, the formal mathematics, you will see that all those three quantities, three objects I've listed here are actually called tensors, right? So a scalar is a tensor of rank 0, a vector is a tensor of rank 1, and a tensor, what we're going to call tensor here, a matrix, if you want, is a tensor of rank 2. And then you can go up further, tensor rank 3, rank 4, and so on and so forth. You'll see that probably if you do general relativity or things like that. Or anisotropy, we also need tensors of higher ranks. And then you can develop an algebra of tensors, which is really nice. There's rules. There are rules for adding, manipulating them. But in this course, we're just going to stick to very simple representations, very simple coordinate systems, only rectangular coordinate systems, and very simple rules of manipulation. Okay, so just to remind you of the conventions for vectors, right? We write vectors, say vector u, in a three-dimensional space. We write it as an array of three numbers, u1, u2, u3, usually like this vertically, or we can write it like this, e1, u2, e2, u3, e3, in a orthonormal vector basis. So these are orthogonal unit vectors. Orthonormal vectors. Right. Until now, we used I, J, K, and X, Y, Z for the components. We're going to use E1, E2, E3. We're going to use indices. It's going to be more general, more handy. We have to draw I, J, K. There's the dot product, two vectors. The dot product, two vectors, is a scalar, right? And it's represented by a dot between the two vectors. If I do u dot v, and you must remember those rules, you can write it like this: u1, u2, u3 dot v1, v2, v3. And the definition is just that we just go multiply the quantity across, right, and add them up. So it's going to be u1 v1 plus u2 v2 plus u3 v2. So that's a scalar. So you will have noticed that I underlined the vectors. I underline it. That underlining means boldface, right? So in the notes you will see that it's boldface. Boldface is really hard to write by hand, so the convention is to use underline. Underline means boldface and means vector.